Welcome to EPG Parashala, the lecture series in computer science for the postgraduate program, and this is the course compiler design and we are on module 31. This module is going to talk about the construction of a directed acyclic graph, how do we reorder the graph and the necessity for reordering, and how do we label the graph. So the objectives of this module are to understand the construction of a DAG for a basic block, and to learn to ensure that the DAG in the context of arrays and pointers, to learn to construct the heuristic reordering for computing with reduced instruction cost, and to label each node with the number of registers required for computation. So a directed acyclic graph is a useful and an important data structure, and this representation is useful for many things, especially like the transformation that is possible on a basic block. So we are going to construct one DAG for every basic block, that is what is your intention. So it can also give detail of how the value is computed for each segment of the basic block. The applications of DAG typically are to look at common sub-expression. So identifying common sub-expression is very easy with respect to DAG. And you can also find out which names are inside the block but evaluated outside, and vice versa. And you can also find out which statements of a block gets their value computed outside the block. Okay. So this is also another extension of the second point basically. So you can observe all these things with respect to the DAG. Now the construction of the DAG basically, leaves are labeled by unique identifiers, variables or constants. And they represent the R values. R is the right hand side values of an expression. Interior nodes are labeled by an operator typically. Nodes are optimally given a sequence of identifiers. Okay. The construction algorithm is the input is a basic block and output will be a DAG having a label for each node containing either the operator or the variables, and for each node a list of attached identifiers are also basically determined and given as output. Now the first thing is you have to look at three cases. The statements can be of the case x is equal to y operator z, x is equal to operator y, and x is equal to y. So three statements are typically possible. You can extend with respect to this, we can also extend it for an if and a go to. So how do we evaluate that also can basically be done. So because this is done basically for a particular basic block, so you can say that if it is if your evaluation is going to be going to if x is less than y, go to 3, if that is going to be your situation, then you can basically transfer control to that particular basic block. But as far as this block is concerned, that statement is basically over. Okay. So therefore we are looking at constructing a DAG for a single basic block. So therefore we are not focusing more on the controlled statements in terms of conditional jump or an unconditional jump. So let us take three cases: x is equal to y operator z, operator y, and y. Now if node y is undefined, okay, you have to create a label y and let it be node of y. So you have to create a new node called as y. And similarly, if node z is also undefined, you create a new node called as z and call it as node of z. Then the next step is for the first case is x is equal to y operator z. So you have to check whether is there a node star available, is there a node operator available whose left and right children are respectively y and z. Okay. If it is there, you have to simply assign the LHS value as a label to the corresponding node. That is, you are not recreating the subtree, you are not recreating a branch, you are not recreating any new node. If it is already there, you simply assign it the tag alone. If it is not there, okay, then you create an interior node called as interior node with an operator OP, and then whose left and right children will be y and z. So you create that particular node. In the case of the second situation where I have x is equal to operator y, you have to again repeat the same process, but you have to ignore that the child z is not going to be available. So you will check whether is there an interior node whose only child happens to be y available. If it is there, simply reuse it. If it is not there, you create it. In the case 3, you assign simply the tag n to the existing node itself. So, it is going to be x is equal to y, right. So, there will be definitely an interior node x available. So, you assign y also as one more tag for that particular node, interior node. So, this is the second step of the algorithm. Then after assigning that, you have to delete x from the list of attached identifiers for node of x, and you have to append x to the list of attached identifiers for the node n and set node of x to n. So, this is what we already said. You will append x to the list of attached identifiers for the node n and set node of x is equal to n. So, this is the simple algorithm, and this is what we already saw in module 29. So, where we had a basic block, this is block B2, which was earlier where we had earlier. So, T1 is equal to 4 into I, T2 is equal to A of T1, T3 is 4 into I, T4 is B of T3, T5 is T2 into T4, T6 is prod plus T5, and finally these were my statements. Now, the corresponding DAG will be constructed for this particular basic block. We will see that in the next slide. So, I have a constant called as 4. I will check whether constant 4 is available. If it is not, I will create. Okay. So, to start with, I have created this 4, and then I have to check whether there is a node labeled I. If it is there, I will reuse. If it is not there, I will basically create. So, I have done the creation here as far as the first statement is concerned. Then that is assigned, that is computed as 4 into I. So, I have computed that as 4 into I, and then that is given a tag as T1. Okay. So, subsequently any T1s if it is available, that should basically be removed, and I have to say that this node corresponds to now T1. Then next node is T2 is equal to A of T1. Now, I will check whether is there a node labeled A, is there a node labeled T1. So, there is no node labeled A, but there is a node labeled T1, which is this node. Okay. So, now I have to form a new node whose operator happens with a subscript operator, whose left and right children are respectively A and T1. So, I have done that here. Now, that is assigned to T2. Okay. The next one is T3 is equal to 4 into I. Now, this is the beauty. So, I will check whether is there a node 4 available. There is. Is there a node which is I available? Again, there is. Is there a node labeled star whose left and right children are going to be 4 in I? That is also available. Therefore, this node will also be appended with the value T3. Now, we know that this is a common sub-expression. A node having multiple tags refers to the common sub-expression, and that they can basically be reused. That is your intention. Okay. So, identification of common sub-expression is going to be a typical and an easy option for as far as DAG is concerned, but it is going to compute the common sub-expression within a basic block, that is called as local identification of common sub-expression only. Okay. So, then we have said it is B of T3, that is also done. Okay. So, T4 is equal to B of T3, that is also done basically, B of T3. Okay. And then T5 was T2 into T4. So, I have done T5 as T2 into T4. Now, I can just keep on expanding like this, and finally, the last statement, I have to simply compute the value of 20, and I will check whether it is greater than 20. If it is there, I have to basically go to another basic block, which I have not listed here. Okay. So, therefore, this is what is the construction of DAG. Now, the situation here is, how do we deal with arrays, pointers and procedures? So, there could be a small problem which could arise. We will see how will it arise and how to handle that problem. So, for example, x is equal to a of I, and then I say a of j is equal to y, and then I say z is equal to a of I. Okay. Now, what does it basically tell you is, you have to compute a of I and put that value into x, store y into a of j, and then put a of I into z. Now, between these two statements, the value of I hasn't changed. So, it is as equal as x is equal to a of I and z is also equal to a of I, right. So, I can say z is equal to x, and then I can say A of j is equal to y. Now this could be a reordering of statement, but what if I is equal to j? Okay, in that case, if I is equal to j, then I am looking at y is equal to A of j here, and y value should be get assigned to z and not the reverse. So therefore you have to have a problem here where if I is equal to j, then the value chosen is different for z, and so while processing an array, what we do is we kill all the nodes labeled with a subscript so that confusion is prevented. Okay, so this is what we basically use to avoid this. Similar scenarios is also adopted for pointers and procedures, and therefore you have to look at some modification to the DAG construction algorithm as evaluation of or assignment to an array must follow the previous assignment if there is one. Okay, this is one alteration, and any assignment to an array element must follow any previous evaluation of A, and any use of an identifier must follow the previous procedure call or indirectly through a pointer if there is one. So this is one more addition, and the last one is any procedure call or indirect assignment through a pointer must follow all previous evaluations of an identifier. So these four techniques are basically used so that the correct value gets assigned in the correct variable, and the DAG doesn't make any doesn't have any ambiguity in showing this as a representation. Now, why do we construct a DAG? The purpose of constructing a DAG is to generate code from it basically. Now this code generation involves the following steps. The first one is you have to rearrange the order of statements if it is possible, which is done using what is called as an heuristic ordering for the directed acyclic graphs. After rearranging it, you have to do an optimal ordering for trees. Now the DAG itself is a tree, right? It's a binary tree. So that is also looked upon to optimally reorder, and we will also label the trees with the number of registers required for computing an interior node. After doing these three preliminary steps, then you perform a traversal of the tree to generate code, and this code generation is based upon the labeled tree. So it depends upon what label you have assigned to a particular node, interior node. Now let us take this. Changing the order of independent statements to efficiently utilize the registers is the primary goal of rearranging. It reduces the final cost of assembly level code. Okay, finally, ultimately that is your situation. Now this is an algorithm which is a recursive procedure. So what it is trying to do is it's going to do a bottom up scan and then start assigning numbers, and then after that it is going to put it in reverse because it's a recursive procedure. It is going to put it in reverse to use to know exactly how a particular DAG should be evaluated. What is my ordering of evaluating a particular DAG? Okay, that is going to be the situation. So while unlisted interior nodes remain, so you have to look at, you have to list all the nodes. That's your ultimate aim. You have to choose an unlisted node n, all of whose parents have been listed. So that is the next one. So you have to choose in a particular unlisted node, all of whose parents have been listed. So to start with, what will you list? You will have to list the root, okay, because root doesn't have a parent. So that is the base condition to start with. Now after that, with n as that listed node, you will check whether the leftmost child of n has no unlisted parents. Okay, so that is your situation, and it is not a leaf. Okay, it should not be a leaf also. In that case, what we do is we have to list that particular node. Okay, while the leftmost child m of n has no unlisted parents, list m. Okay, and n is, you have to change n and m. Okay, and then you basically do a you finish it, and then you have to loop again here. Okay, so after listing it, this is your procedure. Okay, it's a recursive call because I am changing the values here. I am not showing it as a recursive call, but it's ultimately a recursive procedure. Okay, so what have I done here is I have numbered the nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So I will first list the root node. Okay, I will first list 1 and then I will check the leftmost child m of n, where m is not a leaf, and if it has unlisted parents, I will list. Okay, so if it has no unlisted parents, I'll basically list. So I'll check the leftmost child. A is a leaf node, so I have to check this node. This node is this node's parent is not listed, so I will go up. This node is a left child of this one. Its parent has been now listed, so therefore I will list 2. Okay, and then I will continue. After listing 2, okay, I will have to basically stop, because all of whose parents have been listed. So while the leftmost child m of n has no unlisted parents and is not a leaf, you list m. So then you will choose n is equal to m. So you will start with this as my root. Okay, this as my root I have to basically start. Okay, so if I continue like that, I will end up in a sequence as 1, 2, 3, 4, 5, 6 and 8. So which is nothing but I will list this first and then this. Okay, so if I have to list 6, its parent has to be listed, so I have to list 5. So 5 is not listed. If 5 has to be listed, I have to list 4, but 4's parent is not listed. So therefore after listing 2, I will come back to 3. After listing 3, now we know that in order for 6 and 5 to be listed, 4 is to be listed, therefore I will list 4. So 1, 2, 3 and 4. After listing 4, I will list 5, okay, because in order to 6 get listed, I have to list 5. So I will list 5 and then 6 will get listed, okay. Then I will not even look at 7, because 7 is a leaf node. Then I will list 8, because all other nodes are done, I have to list only 8, okay, because 8's parent is 4 only, so that has been listed already, therefore I have to list that. Now I start with 1, I have to keep traversing leftmost child, this is a leaf, so I have to list 6. In order for 6 to be listed, 2 and 5 should be listed. Now 2's parent is listed, therefore I will list 2. I cannot list 5 also, because 5's parent is not listed. So after 2, I will terminate in the inside while loop. I will come out of it and then this will list 3. Okay, this point will list node 3. After listing 3, I will enter the loop. So that will list, that will try to list actually 6, but 6 will have to start listing 5. It's not listed. Then I will list 4 at the outside the body of the while loop. After listing 4, I have to list 5, which I can do. After listing 5, I can list 6, which is again I can basically do. And then these 3 are leaf nodes, so I will come outside the while loop. So again I have to go to the main while loop. In that case, I will basically list the node 8 as my last resort. So I have to list 1, 2, 3, 4, 5, 6 and 8. That is my listing. So after doing this, what I will do is I will reverse the sequence. So I have to reverse the sequence as 8, 6, 5, 4, 3, 2, 1. Now this means I have to compute the node 8, followed by node 6, followed by node 5, then 4, then 3, then 2 and then 1. So if I have to compute node 8, this is nothing but some T8. I will assign the variable as temporary variable as T8. T8 is equal to D plus E. Then I have to compute T6. So T6 is equal to A plus B. Then I have to look at 5. T5 is equal to T6 minus C. Then I have to do T4. T4 is equal to T5 multiplied by T8. Then I have to look at 3. T3 is equal to T4 into minus E. And then T2, which is T6 plus T4. And finally T1 is equal to T2 multiplied by T3. So that is what we are going to look at here. So evaluate T8 first, then T6, then T5, then T4, then T3, T2, T1, and that is going to be your ordering of sequence. So after ordering, now this sequence can be used for generating your final code in terms of move instructions and other stuff. Now to do that, again I will require labeling of the nodes. Now, labeling will be done with respect to determining how many registers are required to compute a particular node, interior node typically. Now, in this context, a left leaf basically means a node that is a leaf and it is the leftmost descendant of its parent. Okay. A left leaf typically means it is the leftmost descendant of its parent, and all other leaves are referred to as right leaves. Okay. Labeling can be done by visiting a node in a bottom up order so that a node is not visited until all its children are labeled. Now, it is just the reverse of what the heuristic algorithm basically said, right? So, we have to list a particular vertex if its parent is visited. Okay. Now, here I have to label a child and then I have to label its parent. That is, I cannot label a node until its children are being labeled. So, this is just the reverse of the earlier one. So, where the order in which the first 3 nodes are created is suitable if the parse tree is chosen as the intermediate code. So, in this case, the labels can be computed as a syntax directed translation. So, this is what one more information available in the textbook. So, if we are going to use this logic, label of n is equal to max of L1 comma L2 if L1 is not equal to L2. That is, L1 is the label of the left child and L2 is the label of the right child. Okay. So, if the labels do not match, so I have to choose the max of the 2 labels and then assign it as for the interior node n whose left and right children are L1 comma L2. On the other hand, I will choose L1 plus 1 if L1 is equal to L2. Labels are matched means then the parent's label will be the left child's label plus 1. Okay. Now, here this is the algorithm. If n is a leaf node, then if n is the leftmost child of its parents, then label of n is equal to 1, else label of n is equal to 0. If it is not a leaf, if it is an interior node, then let us say n1, n2 etc. up to nk be the children of n ordered by label, so that label of n1 is greater than or equal to label of n2. So, the left will have basically a greater value compared to its sibling. Okay. Label of n is equal to max of label of ni plus I minus 1. Okay, this is what we said. So, end. Okay. So, this is incrementing by 1 or finding out the max. So, in that case, this is a leftmost child. So, our strategy is the children should be labeled before labeling its parent. So, I will first label all the leaf nodes. So, this is a left child and this is the right child. So, left means 1, right means 0. So, here left is 1, right is 0. This is an interior node, T2 is an interior node. It has got 2 children, left and right. So, if their labels do not match, it is max of the 2. So, therefore, 1 comma 0 max is 1, it is assigned. E happens to be a left child of T3. So, therefore, it is assigned a value of 1 and T3 will be now computed as L1 and L2 basically matches. So, therefore, it is L1 plus 1 that is available in T3, and similarly 1 comma 2, okay, 1 comma 2. So, I have to choose the maximum of the 2 values if they do not match. So, that becomes 2. So, root can be computed with at most 2 registers is going to be the conclusion. Now, typically for computing the label, you can use post order traversal, and node A is labeled once, 1 since it is the leftmost leaf node. This is what we have just now seen, and B is labeled 0 as it is the right child, and parent of A comma B is assigned a max of 1 comma 0 which is 1. Then the labeling is carried out till the root and the value of at a node indicates the number of registers required to compute the particular node. Now, on to summarizing this particular module, we have seen the construction of DAG. We have also seen the construction of DAG in the context of arrays and pointers. We have also seen the heuristic reordering of statements for reducing the instruction cost, and the labeling algorithm is also defined and used here, which requires to identify the number of registers required to compute a particular interior node. Now, the heuristic reordering observation can be, the heuristic reordering is going to be under the principle that the parent should be listed before its children are listed, or I can say before listing a particular node, all of its parents must be listed, And the labeling algorithm is on the basis that when I'm trying to label interior node, its children should be all labeled. Okay. So this is the strategy used by these two situations. Now with this as a basis, the next module will basically take into account this labeled heuristically reordered DAG as input and generate code based upon that, which will be a DAG based code generation algorithm. Thank you.